Thank you, everybody, for joining us. This is now the 1st of January 2020. Happy New Year to everybody. And once again, I have to say thank you to all our mentors who worked really hard throughout last year and will continue to work hard now. Today, we're lucky to have Hany Elbardesy from Cork University Hospital, who's going to talk to us about research methodology and statistics. And one of our other mentors is Amjad Medina. He's joining us as well today, who will help us with the Viva sessions in the later part of this presentation, which will not be recorded as per standard. We'll also have Mustafa. Sorry, apologies. We'll also have Fuad joining us soon as well. Hany, if you would like to start.
Okay.
Thank you very much. Mustafa Elbardesy is also one of our mentors who's just joined us. Thank you.
Orthopaedic registrar in Cork, in the south of Ireland. So our topic today is the statistics and the research methodologies. So all the views here are my view, and no interest to be declared. So I will start with data, which the statistic in general is a kind of terminology. So you have to know the language of statistician and to do with any research. So the first thing is the data. What is the data? Is observation of variance. So we'll go. So your data may be numbers, maybe words, maybe like figures. So if it's numbers, so it be numerical, like blood pressures, like visit numbers, or maybe categorical, like mild, moderate, severe, like this disease stage, like FRCS stage. All these things are categorical. So the next step, you start you put your data in a graph, and you start to interpret this graph. And if your data is normally distributed, so you will find this curve, which is like a bell-shaped curve, and being described by Carl Friedrich Gauss, who is German mathematician, and who describe if this normally distribute our data, it would be like a shape of the bell, and this is named after him. But sometimes this data may be skewed to the right or the left, and you have a tail. So for an example, if you are doing an ACL reconstruction, commonly is done among young age group. So you will find the tails with a less number of data to the right, because with the extreme of age, no much ACL reconstruction, and that's called positively skewed distribution. And the reverse in the total hip replacement or joint replacement, we do that mostly in old age groups. You will find the tail to the left, because in younger age groups, you will do a less number of total hip replacement or joint replacement. So next, how to measure the tendency, the central tendency of your data after you redraw your graph. So you have three definitions, three terms to know. The first is the mode, which is the most frequent data. For an example, the most frequently days of stays for your hips fracture patient is about 1 week. But maybe the discharge starts from 2 days, maybe to 1 month. But in 1 week, most of your patients being discharged from your hospital. So 1 week is the mode. And the next is the median, which is a 50%. You're not concerned about the most frequently, but in 50% of the patients, say example, if you have a 100 patients, so the 50% you will be discharged maybe in 2 weeks. So that is the median. And the mean is the average. So we'll calculate, you will do the sum of all discharge for all your patients and divide that by the numbers, and that is the mean. Okay, if your data are normally distributed, the mean and the mode and the median should be the same. And this is a graph here. So the first one in the upper one is the median and mean. It's one line, so it's normally distributed. It's a bell-shaped curve. In the lower one to the left side, there is a difference. In the same in the lower one on the right one. These are different distributions. If your data, you'll find the mean and the median and the mode is not the same. You have three lines there. Okay, so after drawing your bell or your diagram for data, so you have a variance, which if you divided your graph to squares, the correct sum of this square is the mean is a variance, and if you got the square root of this variance, that is a standard deviation. So one standard deviation is about 68% of your data, and 2 is 95% of your data, and 3 standard deviation, as you can see here in the graph, it's about 99.7%. So in 95% of your data, it's only 2 standard deviation, and that is very important because the next step will show the confidence interval. The confidence interval, you like include only 95%, which is 2 standard deviation for, of each side of the mean, and that is a confidence interval. So it is the interval that include value of probability 95% or 2 standard deviation. And the important in the confidence intervals, if you have your sample size with high number of populations, so we will find your confidence interval, the 95% will go back here. You will find the 95% is a narrow. You will find this line, you will be narrow because you have a large sample of size. If you have a small sample of size of populations, you will find this 95% wide. And that is the difference between narrow and wide confidence interval. So after collecting your data, how to interpret your data? So the next step, what is the null hypothesis? So its assumption is made that is the difference seen occur by chance. There is no difference. With any difference, you detect it's only by chance. So how much any difference or any something you get it in your data by chance, that's called p-value, is a probability occurred by chance. Usually we accept less than 5%. That is a p-value. So the lesser the p-value is, the stronger the evidence, because if there is like any value by chance is less, that means that you have strong evidence, and vice versa. So in orthopedic, we accept up to 5% of p-value, and you will find this number in all of our research, like v equal 0.5%, 0.001, but you will never find it more than 1%. So next, there is error. So there is a type 1 and a type 2 and type 3 error. So type 1, you will incorrectly reject the null hypothesis. So null hypothesis, we say that is assumption that anything in your data by any difference by chance. So if you incorrectly rejecting this hypothesis is a type 1. If you incorrectly accept the null hypothesis is a type 2. And there is a rare type called type 3 when the researcher correctly rejects the null hypothesis but incorrectly attributes the causes of that. And that's type 3. So just 1 second. So next is the power, is a probability of finding significant association if it's truly exists. So like, for an example, if you have a drug or medications, treatment for osteoarthritis, and you'll compare this medication against placebo or nothing. So you measure how much significant association or any like a change happens by your new drug or new medications. That is the power. So the stronger the effect, the more the power. If it's truly exists. And estimation of the probability of the study will be able to detect true effect of the intervention. And what is power? Power is 1 minus type 2 error. So, and another thing is power analysis. And our analysis is a method of determining the number of subjects needed in a study. So, and this is if you are going to do a research about something, you have to know what is the exact number needed to detect valuable to be for your research, and that's called power analysis. How you can get that? There is a lot of programs, or you can seek the assistance of a statistician to help you to get that. But there's a lot of programs you can use. You can enter your prevalence of your disease, your incidence, your confidence intervals, and the program will get you the number required for your research. And factors affecting your power analysis is the size of difference between the means, the spread of data, the acceptable level of significance with the p-value, sample size, variability in observations, and experimental designs like within subject versus between subject, and type of data. Is it parametric or non-parametric? It's number or figures or according to that. So next, what the study design? You have an observational or experimental. So like observational, like the investigator observe, like polyethylene after pulmonary embolism after total hip replacement. So you observe the complication of something. Experimental, no, you apply maneuver, you observe the outcome. So you'll give the patient heparin versus something to see the DVT prophylaxis. So you will apply, you will give something, you will give a new drug, new total hip, new prosthesis, new something. That's experimental. And there is a study timelines. If your data, collection of your data from the past, it is a retrospective. This is from we are going to start to collecting the data in the next 5 years. It will be prospective study. Or at the meantime, it's a cross-sectional study. So examine a patient or event at a one point of time without follow-up. So for an example, you will see the patient in the fracture clinic today. That is a cross-sectional study. So what is the significance of testing? To test for statistical significance, think about the following. What type of data have been used in the study? What is the sample size? Are the groups distributed normally or not? Do the data need to be transformed so that we can make normality assumption? Are the group interdependent or not? And we'll go again to the parametric or non-parametric test. So parametric test assume the data were sampled from normal population, and the observation must be independent, and the population must have the same variance. So there is specific characters for each test you are going to use, and this is mostly, it's very common in the MCQ. So there is few different type of test. So the first one, which is a pair T-test. So you will see the systolic blood pressure or blood pressure before and after. So pair of observation on a single subject. So blood pressure before and after. It's only that is the pair T-test. If there is a multiple observation, you will something ANOVA or one-way variance test. And here it is the pair T-test of the of before and after. The next is unpaired T-test. The unpaired T-test can be used by two random samples. Like for this example, will the mean of two independent samples, the birth weight in high standard and the low socioeconomic status. So you have two independent samples. So you have to use unpaired test, not the pair T-test. Chi-square test. This is if you are testing for qualitative data, the test is unreliable if any expected value is less than 5. So in this scenario, you'll have to use a Fisher exact test. But in chi-square test, so we can examine like boys and girls, blue, green, pink, color of eyes. So you have more than one variance. and that's chi-square test. Next, in the research, what is the level of evidence? So the first, we'll start with a systematic review of RCT or randomized controlled studies. This is the highest evidence. Next to it, it is a randomized controlled trial. Then well-designed controlled trial without randomizations. Then well-designed case study or cohort study. Then say a qualitative study or expert opinion at the base of the pyramid. So we'll start with the systematic review and the meta-analysis. The meta-analysis is a quantitative, in one word, is a quantitative estimation of the study. So it is a statistical analysis that combines the result of multiple scientific studies that address the same question. For an example, arthroscopic versus mini approach for rotator cuff repair. So you will go through all randomized control studies in the past, and you will collect the data together, and you will do your meta-analysis. So this is Prisma chart. This is the first step in the meta-analysis. After going to the websites, the PubMed and all websites to see how many studies like have the same topics, you will do Prisma charts. The first, you will get the whole studies here, and you will start to exclude studies. So and end by there. You will exclude all studies according to inclusion and exclusion criteria for your meta-analysis. And then you will do a forest plot. So you will put your data from all your studies, and you will find that. And sometimes this forest plot maybe appear in the exam, and you ask you to interpret that. So we will start from left to the right. Here in the left is the name of the studies, like Jonathan et al., Low et al., and so on. So next is N is the number of patients. So this is the study compared between reverse shoulder and hemiarthroplasty. This is a meta-analysis about that. We'll go there, and you will find like a squares and line. The line here is a confidence interval. So the narrowest line is the narrowest confidence intervals, and the widest is wide confidence interval. And the square here is the weight of the study. So the bigger the square, the more weighted the study. And you have two here. You have a 0 at this here, and you have to the right and the left. So all study in the right in favor of reverse shoulder, and all study in the left here are in favor of hemiarthroplasty. So if you ask you to interpret, so more you study, more the studies are in favor of reverse shoulder arthroplasty, and almost most of the study are the same weight with a narrow confidence interval. And there is another forest plot. You see here, no, there is one study in the left. So this study in favor of the control, and this one, and you have this here by Adam, is the big square. That means more weighted study. And this is study here by Orage 36. You'll find how wide is the confidence interval and how small is the square. So this less weighted study. So that is the forest plot and how to interpret that. And we'll go there. You'll find here the word odd ratio. So the next question will be, what is the odd ratio? So the odd ratio is a probability of having risk factor in those who developed conditions. So if you have 100 patients who are smokers, 30 of them died or got lung cancer. So what is the odd ratio? The risk ratio is 30 out of 100, so 30%. The odd ratio, no. So you will take the 30 from the 100, it will be 70, and you will divide the 30 by the 70. That is the odd ratio. Okay, so remember this example about smoking and lung cancer, and 30 and 100, and how to remember the odd ratio. Okay, so here this is another forest plot, and sometimes you may ask you about this number here. You find here there is a small number, this I2 equals 0. What is that? It is the heterogeneity. So what is heterogeneity and what is the importance? Heterogeneity is very common problem among meta-analysis. And when you are trying to combine studies that not matching with each other, so remember, you can combine apples, whatever the colors, like green apples or red apples, but you couldn't combine orange and apples like that. So we accept in the heterogeneity to be from 0 to 25%, and that is the low heterogeneity. It's a medium from 25 to 75, and it's very high after 75. So if you find this I will go back here. If you find if just from the forest plot, if you find the I2 here, it's like 96%. You will know that this meta-analysis is not good. And this author combined like a study not matching with each other. And this is the review manager. It's a very common program if you want to do like any meta-analysis. That's free, and it is a Cochrane review website. And what is systematic review? If we say it about the meta-analysis, it is a quantitative. The systematic review is a qualitative. So we'll go deep through each study and to identify the methods, the populations, and everything in this study, and you write your review. And that is why most of our studies meta-analysis plus systematic review. Most you combine both systematic and meta-analysis. So next we'll go to the randomized controlled trial, which is in the top after the meta-analysis. Randomized controlled trial in the top of the evidence. So definition. So what is the randomized controlled trial? It's a group of patients are randomized to either receive or not receive an intervention. Like you have an osteoarthritis, you will divide the patient. Some group of patients will receive your medication, your new drug, and the other patient will receive placebo, and you will combine the result between both. And here the word is randomized. So what is the randomization? Randomization is you have to ensure that all prognostic variables, both known and unknown, will probably be distributed equally among the treatment groups, and this avoid bias in the treatment. So to be sure that the patient involved in each group should be randomized, because sometimes if you are going to do study for a new prosthesis or new hip replacement, and you choose your patients, young patient, fit, skinny patient, you avoid all obese patients, all that are biased. But if you have to do a real controlled trial, your patient, your sample, you should be randomized. And there is a different ways of randomization. The first one is a sample. You ask the computer by the days, the weeks, like patient admitted in the first, second, fourth, sixth, and so on, will be in the group A, and the patients coming in the third, fifth, seventh, and so on in the months will be group B. This is a sample. And the next will be stratified. Like you will ensure equal distribution between treatment among age, sex, everything. That's stratified. And block, you will do 2 blocks with a number, and in each block you are sure that you have the same equal number of patients, equal number of age, or equal number of sex. So that is the best one. Okay, so next, so because it's the heavy meal, so I divided into 2 lectures. So the next lecture will talk about the bias, other type of study like cohort study, case control study, case series, and critical appraisal, the phases of clinical trials, how to conduct trial, how to conduct research. We'll speak about screening tests and survival analysis like Kaplan-Meier survival analysis, and funnel plot as well. Okay, thank you very much.
Thank you, Hany. Anyone have any questions? So one of the questions is from Atef Mahmoud. He's asking, he thought level 1 evidence was meta-analysis.
Yes. Meta-analysis of well-done randomized of RCT is the best evidence, because if I have like 5 well-done randomized controlled trials, I combine it in one study in meta-analysis, that is the best evidence.
Thank you. And the question I would like to ask you, if you don't mind, is could you explain the connection between heterogeneity and relation to I2, as you showed on the...
I2 is the most common way, which is in the RIVMAN, which is the most common program used in meta-analysis. RIVMAN, so when you put your data in this program, so the I2 is the measure of heterogeneity. So if it's I2, it's 0, 25, 30, that is the measurement of your heterogeneity.
So the lower the I2 number, the
best. From 0
higher
to 25, yeah, 0 to 25, that's low. 25 to 75, medium. More than 75, it's a high.
Okay, so the higher the heterogeneity, if you say high heterogeneity, you're saying greater than 75%.
Yeah, yes, that means that
I2 number is low.
Yeah.
Okay.
That means that your study is like orange and apples, not apples.
Okay, that's good. Okay, thank you. The next the next question is, what added information does confidence interval give you compared to standard deviation?
Okay, if you did a study, if you did a study about six patients, and you will give me the complication rate is 0%. Could I rely on this? Your sample size is only 10 patients, so I couldn't rely on that. How I can know from like interpreting your graphs that your sample size is low, your confidence interval, which is determines the certainty of your result, is wide or narrow. So that is why we use a confidence interval. Another example, if you started your study with 100 patients, and you got, for example, for a new total hip replacement, and you did a revision in the first 2 years for 25 or 30 patients, and you excluded these 30 patients that you did a revision from the end result. So for an example, you are measuring the Oxford score pre-operative and in 2 years or 5 years for your new hip replacement. And you started your study with 100 patients. And after 2 years or 5 years, you give me like only follow-up in 50%, only 50 patients. And you excluded 30 patients, you did a revision, and 20 patients, loss of follow-up. That is very wide confidence intervals, and I will know that.
Okay, that's good. Another way of describing the confidence interval is, for example, if I told you that there's a 10% risk of heart attack associated with breathing air in an inner city compared to air from a beach, my confidence interval is 9 to 11%. That's a very narrow confidence interval, so you can be reliant that that number is correct. But if I said to you my confidence interval is between -10 and 15%, that means it actually might be even healthy. The possibility is the number, you might be even healthier than air in a city is better for you because you have a -10% risk of a heart attack. However, that might indicate that you have a small number of patients and therefore your confidence interval is really big, or it's a spurious connection.
In my comment, for thing is to know the definition. Once you start with the definition of any topic, if you are asked about a p-value, you need to know what's p-value. If you know the definition for FRCS, you are almost halfway through your pass, and then you can negotiate about the discussion later on. I think even the examiners are not, they're not kind of very, they don't get hold of they don't have a very strong grip of statistics. So know your definition about anything. Like if you are asked about the standard deviation, once you know what's standard deviation, you can say the definition, and then you can build your discussion afterwards. But thank you very much for the very good presentation.
Thank you, Amjad.
And for one point for me, like, I think it's a difficult topic and you covered it very well. Again, what Amjad was saying, if you get an opportunity to draw something, just draw it at the same time. So like if you are lucky, they ask you about sensitivity and specificity. So as you are speaking about them, just make that like the simple 2x2 chart and explain accordingly. That will save time and also give good impression to the examiners that you know the subject well.
Very much to all the mentors, also especially to Hany Elbardesy, who prepared an excellent presentation. We look forward to hearing the next one. We'll stop the recording now. Viva sessions will start soon after this. These are not recorded, so please do stay on.